Hello, everyone. So, if you have worked with Rust really at all, you've almost certainly run into traits. In Rust, traits are how we do polymorphism. So, if you want to define a set of shared behaviors that any type can have, you use a trait. And that way, you can declare that, say, a function accepts a generic type that enforces a trait bound, which means that you can pass any type in there as long as it satisfies that trait. It's really important when you're working with traits, though, especially in Rust, when you're working with traits, it's really important to understand the implementation of those traits on that type. So if you're working with a type, but you want to access a trait method, for example, it's really important to understand how that implementation works, because the actual trait implementation might be different based on whether or not you're invoking it on a reference of that type or an owned value of that type. Now, I was going through my notes from a project I closed out a while back, and it was a fairly long-running project, a lot of big changes. And as part of one of those big changes, I actually introduced a really silly bug that I should have known better about, but almost certainly was doing a little bit of copy pasting just to save some time. But in addition to just like being more careful about that, I also found it to be a pretty interesting illustration of why you need to do what I said before, which is that, again, you need to really be careful about the specifics of the trait implementations that you're relying on. So the program you see on the screen is just a simplified version of this. You'll see we have a function getHeaderMap. This returns a header map from the HTTP crate. If you've worked with Rust, if you've worked with HTTP in Rust, you've almost certainly used this, either directly or indirectly. A header map is effectively a data structure within the crate that stores headers from an HTTP request or response. And if you're not accustomed to seeing this, it might not be obvious what this is. So for a very simple HTTP request, you'll see something like get root document, and then you'll see the HTTP version. This is just HTTP 1.0. Then you'll see headers following this. So these are just key value pairs, right? You'll see a host header typically, example.com. You might see, say, like an auth token kind of thing. So again, very contrived, but auth super secret token, something like that. And then you'll see the actual request body. So these are the headers. We have two headers here, host and auth. In this example, what we're doing is we are injecting three headers to the header map. Now, a few disclaimers about this specific example. You'll never see multiple host headers, so I'm just using this just as an illustrative example. You will never practically see multiple headers that use the host key, but I'm doing it here just, again, to illustrate this point. And I won't even get into all of the nuance on when the other use cases where you would use multiple headers with the same key, the security implications thereof, and all of that. The TLDR of all that is HTTP allows it, and so anytime you're working with a library that that allows you to work directly with sort of HTTP concepts, you'll need to account for this. So when we are producing this header map, we're injecting these two headers with the same key but different values. So first example.com, second example.com, and then just for good measure, there's a content length header in there. So again, very contrived example, but I think it illustrates the point very well. So then you'll see up on line 4, we're calling this function, we're putting it into a variable headers, and then we are iterating over headers. Within this iteration, you'll see that we're checking for the presence of a sum, and if you look at the little type hint here, you'll see that when we do this iteration, the type of the type of the iterator is a tuple containing an option of header name and then a value for the header value. So that's why we are checking for sum here, and then just printing it to the screen. So if you would like to think through this a little bit, I would recommend pausing the video here and see if you can tell what will be printed once we run this program. Cargo run, you'll notice that we actually see just one, and we only see first example. So what happened to second example? We see content length, so we don't think like the iterations like ended early, so something left second example out. Now, of course, immediately your thoughts probably go to line 9. There is a conditional that changes whether or not we've printed something to the screen, and so if you are looking at that, you'll correctly assume that perhaps the option is yielding none for that header. But the question is why? And again, highly contrived example. I think one of the reasons why one of the reasons why I probably introduced this bug in the first place is if you call the get method out of a header map, that actually does return an option, and there it's a lot more intuitive. Why, right? You're sort of saying like, I want to get a header out of an HTTP request or response. I want to get the value for this key that I know. Does it exist or not? And so if it does exist, it will return some, and if it doesn't exist, it will return none. I don't remember specifically, but I'm assuming that that's why I introduced this bug in the first place. Again, very lazy copy pasting. Don't do that. But in this case, I think it's pretty clear that it's not quite that, because we're not checking membership. We're iterating over the header map. So it's not as if we're iterating, like it's not as if as we're iterating over the header map, we're iterating over headers that don't exist, right? The implication, of course, is that all of the headers, each of the items in the iteration that are yielded to us exist in the header map. So what does this option do? So if you go over to the documentation for header map, you'll notice that if we go scroll down to the left, you'll see the trait implementations for, did I have them in front of me? I always forget how, yeah, trait implementations. So trait implementations are, again, the implementations of various traits for this type. Now, if you just look at the left bar, you'll see into iterator is listed 3 times. So you actually have to click to see exactly how it's implemented and to see the differences. Once you do that, you'll notice that each of these implementations aligns with the 3 ownership modes of Rust. And just in case you're not aware, in Rust, you can refer to a type by reference, by mutable reference, and by an owned value. These are sort of like the 3 modes for working with Rust. It's just a key. It's a sort of a key concept within Rust's ownership model. Now, as I mentioned at the top of this video, this is one of the reasons you have to be kind of careful about this, because you might sort of, I think, other languages don't make this as obvious, where if you're using some sort of an interface, or any similar like polymorphism mechanism, this level of detail might not be something that's exposed to you. But of course, Rust being the very explicit language that it is exposed to you here, and it really matters. So each of these implementations aligns with one of those 3 modes. This first one is the trait implementation for when you're working with a reference to a header map. This is when you're working with a mutable reference to a header map. And this third one is when you're working with an owned value. Now, I think the fact that this has a lot more text and also some actual examples sort of helps to hint to you that semantically this particular implementation is a little bit different from the other 2. And just to go back to our code, you can see on line 6, we are iterating over the owned value. We're not specifying a reference here. We're simply saying headers, and so we're actually iterating over the owned header map in this case. So back to the docs. What this says is it creates a consuming iterator, that is one that moves keys and values out of the map in arbitrary order, and the map cannot be used after calling this again. You've moved the values out. Now here's the interesting part. For each yielded item that has none provided for the header name, because again, the type for this, and just in case you're not aware of the way that this trait is actually defined, it has 2 associated types, one of which is item, and this is again just the item is what's yielded to you at a given iteration, and then into iter, which is it's just another associated type that's part of this. But the interesting part is the actual item, because again, this is what's yielded to us. So since we're yielded an option for the header name and then T for sort of any type that you want to store as a value in this header map, we have to check the option. And so this paragraph here is interesting because what it's doing is it's explaining when you should expect to see a sum versus a none here. And so it says for each yielded item that has none provided for the header name, then the associated header name is the same as that of the previously yielded item. The first yielded item will have header name set. So what's the fix? Well, in this case, there were a few reasons why, in my case anyway, this wasn't a huge problem. One of which was that I actually didn't care that the header map was being consumed. I wasn't using it afterwards anyway. And of course, if you're doing something silly from a borrowing perspective, Rust will obviously let you know. And also in this case, the service that I was making this change to actually didn't support multiple headers with the same key anyway. It just wouldn't ever happen. I won't get into the details of why. It just literally it wouldn't be possible. And so that's one of the reasons why this never happened. And so from a practical perspective, the option that's being yielded in this iterator was always sum. But it is semantically incorrect to do it this way. And so the more semantically correct thing, at least in this case, if you're really just trying to iterate over the headers and maybe do something with them, maybe move them into another data structure or whatever you need to do, it's probably appropriate to either iterate over the owned value like we're doing here, but then keep track of the last time you retrieved sum, and make sure that any subsequent header where that item is a none value, you've kept track accordingly. So you're respecting the semantics of the implementation. Alternatively, you could always just iterate over reference, and now you're using a totally different trait implementation. So now we need to go back to here and here, and then we can save this, and now we're just sort of iterating over the headers by reference. So then if we run this, you'll see that we're actually getting all 3 headers out because we're not really doing anything to filter them because we don't have to, right? The actual return, the actual iteration, the yielded type is simply header name. It's not actually an option anymore. Anyway, a little bit of a contrived example and an interesting view, I think. It's sort of like a case study in why it's really important to understand the specific trait implementations you're working with. And so, yeah, being aware of how these trait implementations work, really important.